All right, so today we're actually going to take a look at energy bar charts, and this is a really good modeling practice to sort of keep track of where is the energy going from inside of a system. So if we have, an object that is held up really high and ends up falling, obviously you guys know it's going to change from gravitational potential energy into kinetic energy, and so this will allow us to sort of create a visual with this to make the equations a lot easier to work with. So I'm just going to flip over to slideshow here and kind of walk you through this. I'll try to go as quickly as possible so you can sort of pay attention. If we look at this, representing energy with bar charts. So I'm going to read this because this actually is kind of important. One thing that is different with energy bar charts from pie charts is that we typically only include mechanical and thermal energy. In our pie charts, we're including a lot more than just that. When we want to designate more or less energy on a bar chart, we show the bars higher or lower. So I'll kind of show you what I mean here in a second. For example, we've seen one way to represent energy flow with our pie charts. We have all kinetic energy. At the top, we have all gravitational energy with the baseball thrown up. And then as it's going down toward the ground, we have obviously a mixture until it reaches the ground again. In AP, a lot of what we'll do is we'll just kind of annotate this with little bars. So for example, when we want to show an object with a small speed, say a bicycle pedaling down the road, we show a bar chart with the kinetic energy EK. And this little bar would represent, all right, that's roughly how much generic energy is, in the bike. If we wanted to say it's moving quicker, we would just indicate, all right, well, the bar is bigger. Notice there's not really any numbers associated with this. It's just a model. This model is representing more as compared to the other one before. So less kinetic energy, more kinetic energy. Sometimes these little dashed lines will be representative of factor changes. For example, if you say twice as much kinetic energy, you'd want to draw that bar twice as high. And then what we can also do is represent if there's more than one kind of energy inside of this. So for example, we could have a person running while crossing over a high bridge when they show both kinetic and gravitational. So here's our kinetic, here's our gravitational. And again, you couldn't really compare these side by side unless you had more information. This one just happens to show, okay, the gravitational potential is more than the kinetic, so they might not be going that fast, or they're very high up on this bridge. Defining the system is really, really important to doing this. So if we actually define the system all the way through, we can talk about things that go in and out of the system. For example, if we define the system so that the earth, ground, and elastic objects are part of the system, then the forces from those objects will not be considered as external forces. So that's the whole idea of basically we have potential gravitational, potential related to elasticity, so our 1/2 kx squared, and we have the totality of that energy represented in the law of conservation of energy. In other words, the initial energy of the system is equal to the final energy of the system, which is something you have known from middle school. So defining the system is actually the O in what we call an LOL chart. We usually represent it as some kind of little circle here, and we'll label it from time to time, and I'll show you an example here in a second. Now, if some sort of energy appears to be leaving the system, so let's suppose, we have some friction that's changing into thermal energy, and so the object loses all of its kinetic energy. And you'll see an example here in a little bit later. We would indicate that that energy is leaving our system rather than going into our system. That energy leaving we'll refer to usually as work, and what we've been doing with our work as we go through this. So here's an example. Toy car is slowing down due to friction. We can define the system as just the toy, in which case the friction from the ground is an external force because friction's not in our system. So our kinetic energy goes from something to nothing. And so we see this energy leaving the system or leaving the car, going into the surroundings. We could quantify that, and we could talk more about this. But if we were to define the system, we could define the system, in this case, the toy and the ground, then now there's no external force. So we'd actually include the friction into what's actually happening. And we'd say, hey, the energy from kinetic and the energy from the thermal friction is part of our initial. And so there would be no work done on the car. If, for example, we have a box that we're going to go from rest and move it, we can have energy go into the system in the form of work. So it is possible to see this arrow going in if this box starts from rest and we're having the rest be our situation. We're saying this is our initial system and the box is then going to start moving. Well, then the energy goes in, aka the work is done on the box. So when we actually include this, we actually know that work is defined as change in energy. Now, we talked about as change in kinetic energy, but really just change in mechanical or the totality of the energy can also be in case. Now, our change in energy is the energy final minus the energy initial. So if we wanted to rewrite this, we could say the energy initial plus the work, which could be negative or positive, depending which direction it's going, is your final energy. So if there's no work done on the system at all, we just look at a system that's changing from one form to the next, and there's no external forces, we'd say the initial energy has to be equal to the final energy, aka the law of conservation of energy, something you've always known to be true. So there's a couple examples in this PowerPoint that go through this and start to talk a little bit about what we're trying to do. So if this object is, a cart on an incline, so we have gravity working, we have friction working, we also have a spring force in place here, and this thing is attached, and we see this displacement. We can always say, hey, you know what? The initial system total energy will be equal to the final system total energy. And that right there is the key to solving these problems, because at some point or another, it's going to ask you about, well, what is the full length of stretch? And you'd have to think about, well, what is the internal energy related to the spring system? So as it goes through this one, and we'll do this one together here in a second, it's going to say, when two places are shown with two energy bar charts, the initial system is always the beginning, and the circle is going to represent our system. And so you see this LOL that exists. The LOL is the actual chart system that we're going to be talking about. Now I'm going to actually clip this here in a second and kind of walk you through the rest of what's happening on here, because it's this car slowing down and we're kind of going through, all right, what will this actually be? And so if we're going to create some sort of a bar chart situation for this, the EK is going to be our kinetic, EG is gravitational potential, and EEL is our elastic potential, aka spring potential. The system that I'm going to talk about right here is going to be the cart, spring, ramp, whatever you want to call it system. Since I'm including kinetic, gravitational potential, and elasticity, I would say my system inside of here is, the cart, the earth, and the spring. So all of those things are internal to my system. So if there's friction or something going on in place, like that would be outside work actually being done. And so if I look at this object, and let's just say, it's starting from rest, then I could say, all right, there's zero kinetic energy in place. It does have some gravitational energy because gravity is working down. And, we could actually figure this out by doing our little components and say, all right, well, the sine of theta FG is how this thing is working its way down due to gravitational. So I'll say, there's some gravitational potential. I'll go to the second mark on here. And then since we're assuming this is actually attached here, our spring force should be pulling against gravity in this case. Because if we really drew a free body diagram on this, we'd have gravity working down, we have force normal working, perpendicular to this on here, and then we have spring force spring kind of working up. Right now I'm not drawing in any kind of friction because I don't really know if there's friction and I want to make life a little bit easier for us. So there's some sort of elastic potential in here, and I don't really know if it's bigger or smaller than gravity. So I'm just going to kind of like mark a spot on here and sort of show what's happening as we go through. Now, these bars, and I'm going to make this a little easier so we can kind of see along the lines here. Let's suppose that this cart is actually moving as it moves down here. If that is the case, we can see it's at a lower height now. So maybe our gravitational potential now has dropped down to 1 bar. It has some kinetic energy because it's actually moving down there, so maybe that went up to 1 bar. And then our spring has actually been stretched. And so if we look at that stretch, if our spring is 1/2 kx squared, we could see with that x change, whatever this was from beforehand, we should have some sort of increase in spring potential as well. So this bar should go up. So if we're starting at 2, 3, 4, maybe we go up to like this little situation. Here's the problem. You just went from 1, 2, 3, 4, 5 bars to 1, 2, 3, 4, 5, 6 bars. You cannot have that happen because the law of conservation of energy states that the energy in the initial system and final system should be the same unless work is being done. So you have a couple options here. Either something is coming in from the outside and pushing into the system, or we'd have to adjust our bars. So let's assume there is no work done to this system. We could just say, all right, there is more spring potential. What if my kinetic is not quite a full bar? So I'll drop my kinetic and I'll say, you know what, some of this stuff on here, my kinetic is going to be about 1/2 a bar and my gravitational potential is going to be about 1/2 a bar, which means that one of the full bars of gravitational potential shifted into our spring potential and shifted into some kinetic and a little bit of gravitational. And if this is confusing to you, it's because this situation is like all hypothetical with no numbers at all. So let's take a look at a more concrete example. All right, so back to the PowerPoint where we left off on here, we can see, all right, this is the one I just kind of walked through on the whiteboard. Let's try this example. So previously we saw a slowing car could be represented by a pie chart in 2 ways, depending on whether we included the ground or the system or not. We can represent the slowing car with an energy bar chart as well. So let's assume first that the car is the system. And in this case, all we have is kinetic energy. So it is very possible in these bar charts that you just have one of these. Initially, the car is going at some relative speed and then starts to slow down. So sometimes it's easier to almost visualize the initial and final rather than the system right away. We'd say it has some kinetic, and at the end, it has some kinetic, but the kinetic is not as much. Well, that doesn't make sense according to the law of conservation of energy, so the energy must have left or gone somewhere. That's what we're representing as this change in these bars. We say the system is our car, and energy is leaving our system. Now, theoretically, we could mark, if we called this 1, 2, 3, 4 bars and called this, I don't know, 1, we could mark 3 bars leaving the system. That would be the work done on the system. And so that work is leaving, so we'd call it negative work, or the energy initial minus the work is the energy final. Since it's just kinetic, it would actually be a relatively easy calculation because we didn't have to worry about any potential whatsoever. If instead, I'm going to kind of skip through this here in a second, kind of just said it, we called the ground and car all one system, then everything's happening internally, including the frictional force. And so we'd have some kinetic energy. We'd then have less kinetic energy. And you're like, well, where did the energy go if this whole thing is the system? It must have been transformed into another kind. And in this case, we're calling it the change in energy, TH, which stands for thermal. And so as the car is experiencing some friction, we're going to see that the surface ground is going to heat up. And that's the dissipated energy. So if we're 4 bars of kinetic and go 2 bars of kinetic, well, then 2 bars of thermal is what we actually transform in there. So it's 4 and 4. In this case, there's no arrow in or out because there's no work being done. Or sorry, I said 3.5 in this case. Because the entire system is the ground and the car. More often than not, when we first start doing these practices, we're going to look at them more like this. And you'll be like, well, is this actually something AP does? And the answer is yes. Here's an example where you can actually see an old FRQ. And in this old FRQ, you can spot, here's kinetic, here's, what looks like potential spring. I can't show you the whole problem because it is protected, but you can see there's a bar chart where it actually gives you spring and it say, well, what's the next step going to look like if we're changing some system on here? So this isn't just something we're doing to kind of get by with the energy, systems and making sure we can understand it better. It's something that AP will actually ask you as well. So what you're going to do with the remaining time on here as you look at kind of the agenda is you're going to actually take this worksheet, and I'm going to go ahead and pull that over. And this worksheet is actually asking you, I think it's just called work energy at the top of it on here, but it's going to ask you to basically start with your force diagrams, think about what's happening, and then we'll construct this energy bar graph or our LOL models. So I'm going to snip this over and just kind of put it on a whiteboard here so we can sort of see this, read this out together. So start with a force diagram. All right, perfect. All right, so I have, in this case, let me actually get my thing actually working here. We have a baseball that is a mass of 140 grams. It's traveling 30 meters per second, and the infielder's glove is moving backwards 35 centimeters when the ball is caught. So construct an energy bar graph. All right, so baseball, we have a glove, and the baseball is going to be smacking into the glove. So sure, I got a mass, I have the 30 meters per second, and I know the glove is going to move. So we're going to have a distance in this case, and I know it's hard to read this, so sorry, of 0.35 meters. All right, so let's just start with what the problem's actually given us. So we have our little picture. I really don't know if I need a free body diagram or a force diagram on here, so let's see what I got. So mass of baseball, I want that in kilograms, so 0.14 kilograms. Ooh, it's getting hard to read. 0.14, there we go. And it's got initial velocity of 30 meters per second. And we know the displacement of the glove with the ball as being caught is going to be 0.35 meters. And I'm just doing my conversions right off the get-go. Construct an energy bar graph for this situation. All right, so that just basically means do LOL. And LOL is going to be all of our energies inside of here so we can actually make some sense out of this. This says nothing about the ball actually falling. It's nothing about a spring. So I'm looking at this and I'm saying, all right, we just have EK. We've got kinetic energy after the beginning here. And so I'd say, all right, whatever I want to call this, if I'm looking at my kinetic energy in this place, you can kind of just arbitrarily give it some bars because the bars are sort of irrelevant to what we're actually asking. And so I'm just going to model that and say, you know what? I've got this amount of kinetic energy. And at the end, the ball is going to stop. And so my EK at the final would just be there. It's like, well, where the heck did the energy go? And the answer is it went into the glove. And so if we say just the ball is our system, we'd say that there's some energy or some work leaving the system. So the work is allowing this to sort of happen. So we'd have some negative work. And so if we're trying to figure out, what is the average force exerted on this ball, well, we would just say, okay, well, work is, force times displacements. And we also know that work is our change in kinetic energy. Kinetic energy is 1/2 mv squared. And our final velocity is 0. So in reality, like if we're really looking at this, our change in kinetic energy would be, 1/2 mv final squared minus 1/2 mv initial squared. And we have the information for mass and velocity, and we could easily figure this out. This would allow us to figure out the overall work. And with figuring out the overall work, we know that the actual displacement, we can work backwards and solve for the force. So it's really not any different than what we've done. It's just kind of tying together with energy. As you continue on with some of these other ones, you'll start having potential. And so you may see that energy is conserved within inside of a system, in which case the kinetic and potential initially is equal to the kinetic and potential finally. And there's no work on the system. But you'll have to kind of keep track of what you want to call the system. But sometimes it is honestly just this easy. There's only one type of energy. Energy is being lost to the surroundings. Good luck with the sheet. We'll whiteboard this out the next day.